The last video was an introduction to the second law. In that introduction, we had talked about how heat transfers from hot to a cold surface. And we had drawn something that looked kind of like this. Actually, I had drawn two, so remember this. I had a hot side and a cold side. And we said, okay, heat transfers from the hot side to the cold side. But then we said, okay, well, what if we want to use that to try and produce some work? So we put this black box in there, and we said that we could produce work. So what we want to do in this, what I'm planning on doing in this video is talking more about the details of what's in this box. And so this is basically going to be a heat engine. So we're going to talk about heat engines. We're going to develop the relationship for the heat engine efficiency. And this is what we're going to eventually use to determine if our process, our heat engine, violates the second law. Because remember, the whole point of the second law is that the first law basically says that we can have a process like this. The first law says that we can have a process that transfers, say, heat from the cold side to the hot side with no work input. And we know that that doesn't happen. The first law also says that we can, say, take heat, so from here we can take heat and translate it or convert it directly into work. And we know that that's not possible either. We need this heat rejection to basically complete this cycle. And we're going to talk more about that in this video and specifically why that is a requirement. And so what the second law does, since the first law says that we can basically do impossible processes, what the second law does is it puts a restriction on those processes. So our overall goal is to determine a way, we want to figure out a way that we can determine if our process or our heat engine cycle violates the second law. So we're going to work on that in the next few videos. In this video, I'm mainly just going to be talking about heat engines and develop a relationship for the heat engine efficiency. And then it's that efficiency that we're going to be able to use to determine if our cycle violates the second law. So what we want to do is look specifically at what's in the box. So we have this box, what's in the box. And probably the best modern fit for a description of a heat engine is a steam power plant. So what we're going to do is look at a steam power plant. And a steam power plant is an external combustion engine. And what's meant by that is that the combustion takes place outside of the engine, and the thermal energy that's released from the combustion gases is transferred to the steam that is the working fluid for the power plant. So I'm going to define the working fluid is basically the fluid that goes through the cycle, and that's going to make more sense in a minute. But let's look at a steam power plant. So first we're going to have a hot side, and I'm going to just call this temperature high. And then we have our sink. So I'm going to put that this is our source, this is our sink, and this has a low temperature. And this could be like a lake. So steam power plants are often located by bodies of water, so like a lake or something like that. And then we have our box that we want to define what's going on in here. So we've already seen, like if we go back to this drawing, we know that there's some heat transferred into this box, heat transferred out, and then there's some work. So let's draw these in. So we have heat transferred in, so I'm going to call the heat transferred in just QH. And this is the adding heat. And then we have heat transferred out, so this is QL. And this is the rejected heat. And then we have our work out. All right, so let's look at what's actually in this box. So first of all, remember this is for a steam power plant. So there's different variations of this, but we're considering just a steam power plant right now. So first of all, we're going to have a boiler And so we're going to be adding heat to the boiler, and basically what that's going to do is convert water to steam. So we have a boiler, and this is converting water to steam. And so then we have steam moving through here, and right here we're going to have a turbine. So the steam is going to flow through the turbine, it's going to cause the blades to spin, and it's going to produce work. And then, remember how I had mentioned the working fluid? So steam is the working fluid in this steam power plant. And so the working fluid is just the fluid that's going through the cycle. And so this is eventually going to form a cycle back to the boiler. So this fluid is going to be flowing through a cycle, and so that's called our working fluid. And so after the steam comes out of the turbine, it's going to go into a condenser, and the condenser is going to reject heat. So basically it's going to remove heat, and it's going to convert the steam back to a liquid. So we have a condenser, and then this is going to go from the condenser to a pump. And so what this pump is going to do is it's going to increase the pressure back to the pressure of the boiler, so then the liquid can go into the boiler, and once again the boiler is going to convert the water into steam. And so we have basically a complete cycle here. And one thing to notice is the pump is going to require some work input, because remember, pumps require work. So the pump is usually attached to the turbine, and it's going to get its work from the turbine. So this work out from the steam power plant is actually going to be net work out. So it's going to be the work from the turbine minus the work that was supplied to the pump from the turbine. And so if we look at these devices, we've already talked about all of these devices individually. That's what we did in Chapter 5 when we talked about the steady flow devices. So we've already done analysis on all of these devices, but what we want to do now is we want to consider this as a complete system. So what we're going to do is look at all of them together as our system, like this. So maybe I'll do this in a different color. So this is our system, and we want to consider all of these as part of our system. And so what we want to do is, the overall goal of what we're doing is we have this cycle where we have this cycle where we're producing work, and we have a heat source, and we have a heat sink, and we want to determine if this violates the second law. So what we need to do is we want to consider the efficiency. And so the efficiency that we're going to consider is called the thermodynamic or thermal efficiency. So this is the thermodynamic or thermal, and this is often just written as TH. And so we already know that efficiency is the desired output over the required input. So if we go back and look at our cycle, our desired output is this work, and our required input is this heat source. So we know what our desired output is, and we know what our required input is. So what we can do is we can write our thermodynamic efficiency as the work net out over the required input, which is QH. So this is the heat input from the source. And what we're trying to do with this, since the work is our desired output, we want to get this work as high as possible. So we want this to be as high as possible. So we know what QH is. So QH is just our heat input. But we want to figure out, okay, well, what is the work net out? Like what is that? So what we can do, if we go back and look at this cycle, if all of these are inside our system, so this is our system, we can just analyze this as a closed system because we don't have any mass going in or out of our system. The mass is all contained within the system, and so we can analyze this as a closed system. And it is true that, like, if we, like, let's say that we just looked at the turbine as our system, that would be an open system because then we have mass flowing in and out, and so we would analyze that how we analyze turbines in Chapter 5, or the same thing for any of these devices. But in this case, we're just saying, well, our system is this entire, is all four components. So our system is a closed system because there's no mass flowing in or out or across the system boundary. So what we can do is we can just say this is a closed system. So here's our system, and it has all of this stuff inside of it, but they're all inside the system, so we don't need to analyze them separately. And so if we just look at our system, this is our system. If we just look at our system, we have some heat in, and I'm just gonna, well, we have some heat in, and this is QH. We have some heat out, and this is Q low, and then we have some work out. So what we can do is we can just apply our energy balance for a closed system. So let's write down our energy balance. So we have Q minus W is equal to delta U plus the change in kinetic energy plus the change in potential energy. Well, the change in kinetic energy and potential energy are just going to be zero because our power plant isn't moving. And we're also assuming that there's not a large elevation change between the different components. If we look at this, okay, well, this is operating on a cycle. And so what that means, so our system is operating on a cycle. What that means is that the beginning and ending of the cycle are at the same thermodynamic state. So the start and end are the same thermodynamic state. So if we look at this change in internal energy, remember this internal energy is a state function, so it doesn't depend on the path that the system takes. So basically, if we're at the same thermodynamic state at the beginning and the end, that means that delta U has to be equal to 0. We can't say that for the work and the heat because we know that work and heat are path functions, and so we can rewrite this minus dW because these are path functions, so they're not going to be 0 because they depend on the path taken, not the state. So this is equal to 0. So then we have delta Q is equal to delta W, and this makes sense that the work would be a path function because if it wasn't a path function, like if, say, work was a state function, we could never get work from a cyclic device because the work would always be 0. And so it's a good thing that the work is a path function. And actually, if we look at this, so let's look at our cycle. So we have, let's say that, so this is a PV diagram. So let's say that this is state 1 and state 2. And so let's say, so for our cycle, we're going from state 1 to state 2. And then, well, so that's part of the process. And then we're returning back to state 1. So this is a thermodynamic cycle. We begin and end at the same state. And so that's why the delta U is equal to 0, because delta U only relies on the state here and the state here. And so if our beginning and ending states are state 1, that means that the change in internal energy is 0. But if we look at the work, so remember PV is work, so let's say, so this is our path from state 1 to state 2, so our work is going to be everything under this curve. And then when we go back to state 1, our work is going to be everything under this curve. So then if we subtract those, our total work is everything in here. So this is our total work. So the work and the heat aren't going to be 0, or the total work and heat won't be 0 for a cyclic device because they're path functions and not state functions. Basically, we have that delta Q is equal to delta U, and we're trying to figure out what the work is. So in order to get the work, we want to integrate over the cycle. So we're going to integrate over the cycle. Remember, this integration just says that we're integrating over the entire cycle. So then if we integrate this, the work net out is equal to QH minus QL. So then if we plug this into, like if we go back up to our equation we came up with for the thermal efficiency, we can plug that net work in, and we already know QH. So if we plug the net work in, we get that the thermal efficiency is equal to, and I'll just rewrite this, so the work net out over QH is equal to QH, so we're just going to plug this in, well, that actually, so QH minus QL over QH. So then, and then if we divide QH out, the thermal efficiency is equal to 1 minus QL over QH. So this is our thermal efficiency for a heat engine. So this is the efficiency for a heat engine. One thing I want to point out with the Q and the W in these particular equations are always absolute values. So basically the sign is included in the equation. And so when you use these equations, you want to use the absolute value of the QH and QL and work. That's a little bit confusing because in the first law, the sign wasn't actually included. So we were putting the sign in based on whether our heater work was in or out. But in this case, you just want to use absolute values of QL and QH just because the sign is included in the equation. So this is a little bit different from how we were using the heat and work in the first law. But basically, if we use the absolute value for QL and QH, this term is always going to be less than 1. So this is always less than 1. And that's because QL and QH are positive because they're the absolute value. So if we look at some typical thermal efficiencies for various types of engines, for a spark ignition engine or a car engine, the thermal efficiency is somewhere around 25% normally. For a diesel engine, the thermal efficiency is approximately 40%. And for a gas turbine power plant, so gas turbine power plant, the thermal efficiency is typically around 60%. So we can't ever have 100% efficiency, and the reason why is because this QL over QH is always going to be less than 1, and so we can't ever have, like, the efficiency is never going to be greater than 100, and it's never going to be 100%. If we look at these efficiencies, even for the efficiency for a fairly high efficiency heat engine is still just over half of that. 60% just seems like a pretty low efficiency. So almost half the energy supplied for even a really high efficiency heat engine ends up as waste. And so one question always is, well, if we go back up and look at this cycle, why can't we just take the condenser out and run this cycle without the condenser? So basically, why can't we just skip the condenser, go from the turbine to the pump? Why can't we do that? I mean, if you think about your car's engine, we already know that if you drain all of the coolant out of your car or all the radiator fluid out of your car and try and run it, it's not going to work. It might run for a little bit, but the engine isn't going to work for very long. So we already have an intuitive sense that we need this heat rejection. But let's look at why. So let's go down here. Why do we need the heat rejection? So basically what we're doing a thermodynamic cycle, and in order for the engine to continue to run, we need to complete the cycle. So let's look at a really simple heat engine that we're using. We're going to use this heat engine to lift weights. So let's say that we have a cylinder and we have a couple stops in here. And then let's say that we have a piston. And let's say that we're using this to lift a weight. So let's say that we have a weight on here. So we have a weight sitting on the piston, and we want to lift the weight. Let's say that we have gas inside the cylinder that's at 30 degrees Celsius. And let's say that we have heat source here that's at 100 degrees Celsius. And so what we're going to do is we're going to provide heat to this gas. We're going to heat up the gas. So that's going to increase the internal energy of the gas. The gas is going to expand, and it's going to provide work, and it's going to lift that load. So I'm going to just say that the Qn is, and let's write this over here. So Qn is equal to 100 kilojoules. Let's look at after the gas has been heated. So we've lifted the load. And so now let's say our piston is right here, and we still have our gas. Let's say the gas is at 90 degrees now. And so we've lifted the load, so now the load is up here. Then let's say that we remove the load. So we take the load off. So now the load's over here, and there's no load on here. Well, now in order to complete the cycle, like right now we can't do more work unless we complete the cycle. And to complete the cycle, that means that we need to return the gas back to 30 degrees. Well, if we don't have a heat sink, let's just say that we have this source, and the source is at 100 degrees Celsius. So in order to complete this cycle, we need to return the gas back to the 30 degrees. So basically what it was at the start of the cycle, because we're trying to complete. So if we have our cycle, so far we've gone from 1 to 2. Well, we need to get back to 1. And the way that we get back to 1 is we need to return the temperature of the gas back to 30 degrees Celsius. Well, if we don't have the heat sink, if we just have this source, we can't return, like we're not going to be able to transfer heat from the gas to the source and return the temperature of the gas back to 30 degrees, because that's going to violate the second law. So if anything, the source is going to continue to heat up the gas, and we're not going to be able to complete the cycle. So in order to complete the cycle, the cylinder needs to be brought in contact with, so here's our gas that's at 90 degrees C. This needs to be brought into contact with a heat sink or lower temperature reservoir. So let's say that we have a 20 degree reservoir. What's going to happen now is heat's going to transfer from the gas to the reservoir. So we're going to have Q out, and we're going to be able to return this gas back to the 30 degrees Celsius. Volume is going to decrease, and so after we transfer the heat out, this gas is going to return back to the 30 degrees Celsius. And now we've completed our cycle. So if we go back up and look at where we started, so we started here. So let's say this is 1, different color. So let's say this is 1, this is 2, and then this is still 2, and then this comes back to 1. So we've completed our cycle. Our gas is now back at 30 degrees, and we can put a load on here again, and then we can once again bring this in contact with the hot reservoir. So now let's say that we've brought this in contact with the 100 degree source, and it's going to transfer heat into the cylinder and increase the internal energy of the gas, which is again going to lift the load. So basically, the reason why we need the heat sink or the heat rejection is because it's required in order to complete our thermodynamic process or our cycle. And if we don't complete the cycle, the heat engine can't continue to run. It's basically going to be stalled at this point, and it won't be able to complete the cycle. So basically, every heat engine must waste some heat energy by transferring it to a sink. So this is going to be a requirement for every heat engine. And this comes back to the Kelvin-Planck statement that I gave you last time. So this basically what the Kelvin-Planck statement says is required. The Kelvin-Planck statement says that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So basically, in our power plant example, we have to have the condenser. Like our cycle isn't going to work without the condenser. And in this simple example here with this gas cylinder, we saw that without the sink, we can't return the gas back to its initial state and complete the cycle. So this heat sink is required, or the heat rejection is required, and so this is a requirement of the second law. So far what we've done in this video is we've proven that we need the heat rejection, and we've come up with an equation to calculate the efficiency of a heat engine. But we still haven't answered the question, okay, well, how do we know if our heat engine violates the second law? So really what we want to do is we want to take this efficiency, so we want to take this thermodynamic efficiency, and we want to determine if our heat engine violates the second law. In order to do that, we are going to need to look at an ideal heat engine cycle. So we need an ideal heat engine cycle. And basically what an ideal heat engine cycle is it's ideal. So an ideal heat engine cycle is the maximum efficiency, so the maximum thermal efficiency that a heat engine can have. Because remember, so even if we have an ideal heat engine cycle, the efficiency still isn't going to be 100%. So what we want to do is we want to figure out, okay, well, what's the maximum efficiency that a particular heat engine can have? And then we want to compare our efficiency to that maximum efficiency. And if we're coming up with an efficiency that's higher than the maximum possible efficiency, then we know that our heat engine violates the second law and therefore it's impossible. So we want to consider the ideal heat cycle. This is the maximum efficiency that a heat engine can have. And so it turns out that this ideal heat engine cycle is what's known as the Carnot cycle. So we're going to look at this in a future video. So we're going to analyze the Carnot cycle in a future video. But basically what we're going to do in order to, so the way to know if second law has been violated is there's a few steps. So the first thing we're going to do is calculate our efficiency. So we have the efficiency for our proposed heat engine. So we're going to calculate our efficiency. And then we're going to calculate the efficiency of the ideal cycle. So calculate efficiency of ideal or Carnot cycle. Based on the heat source and heat sink that we're using, we can calculate what the efficiency of an ideal Carnot cycle would be. And then what we're going to do is we're going to compare our efficiency. So we have our thermal efficiency. We're going to compare that to the, I'm going to put this, so we're going to compare our efficiency to the efficiency of the Carnot cycle. And then what we're going to do is we're going to see, okay, well, we know that our thermal efficiency has to be less than the thermal efficiency of the Carnot cycle, because if the Carnot cycle is the maximum efficiency you can possibly have, or the ideal efficiency is the ideal heat engine is the maximum efficiency you can have, we know that our efficiency for a real heat engine has to be less than that. If we calculate that our efficiency is greater than the Carnot efficiency, then we know that this is impossible and it's going to violate the second law. So what we're going to do is in a future video, we're going to analyze a Carnot heat engine and look at how to calculate the efficiency for a Carnot heat engine. And then we're going to look at how we would compare our efficiency for, say, our real heat engine to the Carnot heat engine to see if our real engine is possible. But before we do that, we first need to define what reversible and irreversible are. And so I'm going to first do a video on the reversible and irreversible, then I'm going to do a video on the Carnot heat engine, and then we're going to look at how we can determine if our heat engine violates the second law.